This is a transistor, the most important electrical component in all of computing. Made predominantly of silicon, which is a semiconductor, transistors have one very important property which makes them super useful for building digital computers. A transistor has 3 wires and is often drawn and represented like this. The wires are called the base, the collector, and finally the emitter. The fundamental property of a transistor is that if a weak current passes into the base and through to the emitter, then a strong current is able to pass from the collector to the emitter. If no current flows through the base, then electricity is not conducted between the collector and the emitter. And here's a single transistor in action. You can see the transistor sitting in the middle here. The collector through this LED is connected direct to power, and the emitter connected to ground here. And over on this side of the circuit, power is connected to this button through this LED to the base wire of the transistor, which will then run to ground. So when this button is pressed, power can run through the button, through the LED, into the base, out of the emitter to ground. Allowing current to pass through the base, as shown by the green light, we can see that current is also able to pass through the collector to the emitter, as shown by the red LED. And when no current passes into the base wire of the transistor, we can see that no current can pass through the transistor from the collector to the emitter either, hence the red light has gone off. As we discussed in the video on representing binary using electricity, we can think about a high voltage as a 1 and a low voltage as a 0. This is the essence of digital computing, and we really use the terms high and 1 and the terms low and 0 interchangeably throughout this video and throughout computing. So let's take a look at the truth table of a single transistor. A truth table is a schematic for comparing inputs and outputs. And in this case, our input is the current on the base, high or low, and our output is the current on the emitter, again, high or low. So if we have a high input on the base, a 1, then our output is also high, also a 1. And if we have a low base, then we have a low output on our emitter. So in this case, our truth table is pretty bland, to be honest. Our input is always equal in value to our output. This doesn't seem very useful, does it? If the output is the same as the input, then what's the point? Well, it's a good question, and the answer is, on its own, a transistor isn't much use. But as we'll see in the coming videos, by combining transistors, we can start to build much more complex logical circuits using these very, very simple and essential electrical components. But a single transistor does have at least one useful function on its own. That is by acting as an amplifier. That's because the transistor takes a weak signal on the base and can convert it to the strong signal coming in from power to the collector and out the emitter, and that is because the collector is always connected directly to power. So if we have a weak current coming in on the base, we can amplify it with this much stronger current coming directly from power, and if there's no current on the base, then we simply output nothing at all. This is a very useful function of a single transistor which a number of circuits make use of. Now we can see this amplification function in action. If we swap this wire out for a 2K transistor, which was a bit fiddly, so now when we apply power to the base, we can see that the current is weakened by this resistor. You can't tell by the camera, but this green light is much dimmer than it was before. This is because the current is weakened by the transistor. However, the red light representing the signal which is input and output, is just as bright as it was before. Again, you can't tell this by the camera, but what that means is that regardless of how strong the input current on the base is, the output current out on the emitter is always going to be high and strong. And we can make use of this technique in any circuit where we want to amplify weak currents. For context, today, computers have billions and billions of transistors inside them, each absolutely tiny, roughly 10 nanometers in size, which is about the size of the width of a strand of DNA. But back in the 1960s, when transistors were much, much bigger, Gordon Moore, one of the co-founders of the chip manufacturer Intel, foresaw the importance of transistors becoming much, much more abundant and smaller. The more transistors we can fit on our chips and into our computers, the more power it subsequently has. Gordon Moore is one of the gods of computing, and through his work at Fairchilds and then Intel, he has and continues to pioneer integrated circuit digital computing. In 1968, he co-founded Intel with Robert Noyce, another computing heavyweight known as the Mayor of Silicon Valley. Moore's prediction, known as Moore's Law, was that the number of transistors in a unit of size would double every year to 2 years, or roughly 18 months, a somewhat self-fulfilling prophecy that has only in modern times begun to wane. This prediction allowed Intel engineers to plan and design ahead, to predict what technology would enable them to do and to build in the years to come. The consequence of Moore's Law is that computers grew exponentially in power and performance and memory sizes, at such an alarming rate that the computers of today are barely comparable to those of even a couple of years ago. Today, we take for granted the power provided by the billions and billions of transistors at our disposal. Moore's Law is hitting some limits today though, and the number of transistors that we can continue to add to our chips and into our computers and phones is slowing quite dramatically. This is because transistors have become so small that they are separated from one another often by just a few atoms. At this nanoscopic scale, they are vulnerable to quantum tunneling. Quantum tunneling is essentially when an electron can jump across a tiny barrier. As you can imagine, this makes behaviour very unpredictable and blocks the way for making even smaller transistors in the way that we currently do. This has caused many to claim that the free lunch is over. Our software isn't going to get faster just because the hardware is getting faster, because the hardware isn't necessarily getting faster anymore. Instead, hardware manufacturers are hoping to leverage concurrency, parallelization, by adding more cores to our CPUs. More chips instead of more powerful chips. And that's transistors, how they work and why they are so important to the computing revolution. In the next video, we'll begin to look at how we can combine these small components, transistors, into much more complex bodies of logic, which in the end make up everything inside our CPUs, inside memory, and inside our computers and phones. This has been 54M, and I'll see you soon.